C# performance is absolutely crucial for delivering an optimal user experience and ensuring system efficiency in modern applications. A slow application can lead to user frustration, decreased productivity, and even financial losses for businesses. Conversely, a highly performant C# application provides a smooth, responsive interface, handles large data volumes with ease, and makes efficient use of system resources, which is vital for scalability and cost-effectiveness in cloud environments. Effective optimization strategies in C# encompass a multifaceted approach, primarily focusing on three key areas. These include meticulous memory management to prevent resource leaks and reduce garbage collection overhead, adopting efficient coding practices that leverage optimal algorithms and data structures, and skillfully utilizing advanced C# language features and .NET runtime capabilities designed for high performance. Mastering these pillars allows developers to build robust and lightning-fast applications. The Common Language Runtime, or CLR, in C# plays a pivotal role by automatically managing memory through its sophisticated garbage collector. This automated process is a cornerstone of C# development, as it effectively prevents common memory-related issues such as memory leaks and dangling pointers, which are often problematic in languages requiring manual memory management. The CLR's garbage collector continuously monitors memory usage, identifying and reclaiming memory occupied by objects that are no longer referenced by the application, thereby ensuring system stability and efficient resource utilization. Understanding the fundamental distinction between stack memory and heap memory is crucial for C# performance. Stack memory is primarily used for value types, such as integers, booleans, and structs, offering extremely fast allocation and deallocation because memory is managed in a last-in, first-out manner. In contrast, heap memory is utilized for reference types, including strings, class instances, and arrays, where objects have a longer lifespan and their memory is managed by the garbage collector. This difference impacts allocation speed, garbage collection frequency, and overall application responsiveness. The garbage collector efficiently categorizes objects into three distinct generations to optimize its operation. Generation 0 is for newly allocated, short-lived objects, which are collected frequently and quickly. Objects that survive a Generation 0 collection are promoted to Generation 1, indicating they have a slightly longer lifespan. Finally, objects that persist through Generation 1 collections are moved to Generation 2, which contains long-lived objects that are collected less frequently but with more significant overhead. This generational approach significantly improves collection efficiency by focusing on the most likely candidates for reclamation. The garbage collector's operation involves three primary phases to efficiently reclaim and used memory. First, the mark phase identifies all objects that are still reachable and in use by the application. Following this, the sweep phase reclaims the memory occupied by the unreachable or dead objects. Finally, the compact phase defragments the heap by moving surviving objects closer together, thereby reducing memory fragmentation and making larger contiguous blocks of memory available for future allocations. This systematic process ensures optimal memory utilization and reduces the likelihood of out-of-memory errors. Identifying performance bottlenecks is a critical step in any optimization effort and can be effectively achieved using specialized profiling tools. Profilers like Visual Studio Profiler, .trace, or Perfview provide deep insights into an application's runtime behavior, allowing developers to pinpoint areas consuming excessive CPU cycles, allocating too much memory, or causing I/O delays. These tools visualize call stacks, memory allocations, and thread activity, making it possible to precisely identify the code segments responsible for performance degradation rather than relying on guesswork. For objective and precise evaluation of code performance, specialized benchmarking tools such as benchmark.net are indispensable. This powerful library allows developers to measure the execution speed and memory consumption of specific code snippets with high accuracy, accounting for factors like JIT compilation, garbage collection, and CPU caching. Benchmark.net runs code multiple times, performs warm-up iterations, and collects statistical data, providing reliable metrics that enable informed decisions about performance improvements and comparisons between different implementations. Efficient memory usage often involves advanced techniques like object pooling, which significantly reduces the overhead associated with object creation and destruction. Instead of constantly allocating new objects and relying on the garbage collector to reclaim them, object pooling reuses a pre-initialized set of objects. This approach is particularly beneficial for frequently created and destroyed objects, such as game entities, network buffers, or database connections, as it minimizes memory allocations, reduces garbage collection pressure, and improves overall application responsiveness by avoiding repeated memory churn. Utilizing span-T and memory-T is a key strategy for highly effective buffer management in C#, providing safe and extremely efficient access to contiguous memory regions. These types allow for zero-copy operations, meaning they provide a view into existing memory without allocating new memory or copying data. Span-T is a stack-allocated type for synchronous operations, while memory-T is a heap-allocated counterpart suitable for asynchronous scenarios. Their use dramatically reduces memory allocations, improves throughput, and enhances performance when working with large data buffers, such as parsing network packets or processing file contents. Stack-alloc is a powerful C# feature that allows for stack-based memory allocation, which is significantly faster than heap allocation for small, short-lived data structures. Unlike heap allocations, memory allocated with stack-alloc is automatically deallocated when the method exits, incurring no garbage collection overhead. This makes it ideal for temporary buffers or small arrays where performance is critical, such as in high-performance parsing routines or cryptographic operations. However, it must be used with caution, as stacked memory is limited and can lead to stack overflow exceptions if too much memory is requested. Avoiding the large object heap, or LOH, is a crucial memory optimization technique, as objects larger than 85 kilobytes are allocated on this special heap. The LOH is not compacted during garbage collection, leading to memory fragmentation over time and potentially triggering more frequent full garbage collections, which can pause the application. Strategies to mitigate LOH issues include breaking large objects into smaller ones that fit on the regular heap, or, more effectively, using ArrayPool-T. ArrayPool-T allows for the reuse of large arrays, significantly reducing allocations on the LOH and minimizing memory pressure. For optimized coding practices, asynchronous programming with async and await keywords is fundamental for building responsive C# applications. This pattern prevents thread blocking, especially during I/O bound operations like network requests or database calls. Instead of tying up a thread while waiting for an operation to complete, async/await allows the thread to return to the thread pool and handle other tasks, improving application responsiveness and scalability. This is particularly vital for user interfaces, ensuring they remain fluid and interactive, and for server-side applications, maximizing throughput. Multithreading with the Task Parallel Library, or TPL, enables efficient parallel operations, leveraging modern multi-core processors to execute CPU-bound tasks concurrently. However, this power comes with the responsibility of careful attention to thread safety. When multiple threads access shared resources, race conditions, deadlocks, and data corruption can occur. To prevent these issues, developers must employ synchronization mechanisms like locks, such as the lock keyword or monitor class, to ensure that only one thread can access a critical section of code at a time, thereby maintaining data integrity and application stability. Optimizing LINQ queries is essential for maintaining performance, especially when dealing with large collections. Key strategies include choosing appropriate data structures that align with the query's needs, such as using a hash set, T, for fast lookups, or a dictionary, T-key, T-value, for key-value access. Crucially, developers must avoid multiple enumerations of the same query, which can lead to redundant computations. Materializing the query results into a list, T, or to array after the initial filtering or projection can prevent re-execution and significantly enhance performance, particularly within loops or when results are accessed multiple times. For efficient string concatenation, particularly within loops or when building complex strings, String Builder is the unequivocally preferred tool in C#. Unlike the string type, which is immutable and creates a new string object with each concatenation operation. String Builder works by modifying an internal, mutable buffer. This approach minimizes memory allocations and reduces garbage collection overhead, leading to substantial performance improvements when appending many small strings together. Using String Builder can transform a potentially slow operation into a highly efficient one, especially in scenarios like log file generation or dynamic SQL query construction. Choosing the right data structures is absolutely critical for optimal performance in C# applications, as each structure has distinct performance characteristics for common operations. For instance, list T provides fast indexed access but can be slow for insertions or deletions in the middle of the collection. Set T offers extremely fast lookups and ensures unique elements, making it ideal for membership testing. Dictionary T-key T-value excels at rapid key-value pair lookups. Selecting the most appropriate data structure for a given task can dramatically reduce algorithmic complexity and improve execution speed. Minimizing boxing and unboxing operations is a vital performance optimization, as these processes introduce unnecessary allocations and performance overhead. Boxing occurs when a value type, such as an int or struct, is implicitly converted to an object or an interface type, causing it to be allocated on the heap. Unboxing is the reverse process, converting an object back to a value type. Both operations incur a performance cost due to heap allocation, memory copying, and type checking. Avoiding scenarios where value types are treated as reference types, such as passing them to methods expecting object parameters, can significantly reduce this overhead. Optimizing loops is a fundamental technique for yielding significant speed improvements in C# code. This involves several strategies, such as reducing computations inside the loop body by moving invariant expressions outside. For example, calculating a constant value once before the loop starts rather than in every iteration. Additionally, ensuring efficient iteration, perhaps by using a for loop instead of for each for arrays or list T, when direct index access is beneficial, can reduce overhead. Minimizing method calls or property accesses within tight loops also contributes to faster execution, as each call adds a small but cumulative overhead. Efficient data retrieval from databases is absolutely vital for the overall performance of many C# applications. Slow database queries can be a major bottleneck, leading to unresponsive applications and poor user experiences. Achieving efficiency often requires meticulously optimized SQL queries, ensuring that only necessary data is fetched and that joins are performed effectively. Furthermore, proper indexing on frequently queried columns is paramount, as indexes allow the database to quickly locate data without scanning entire tables. Regularly reviewing and optimizing database schema and queries can dramatically improve data access speeds. Implementing robust caching mechanisms can drastically reduce the need to recompute or refetch frequently accessed data, leading to significant performance gains. Caching stores data in a temporary, fast access location, such as in-memory or a distributed cache like Redis. When data is requested, the application first checks the cache. If found, it's retrieved much faster than from the original source, like a database or external API. This reduces latency, decreases load on backend systems, and improves overall application responsiveness. Careful consideration of cache invalidation strategies is essential to ensure data freshness. Using value types or structs for small, immutable data structures can significantly improve performance by allocating them directly on the stack rather than the heap. This stack allocation avoids the overhead of garbage collection and reduces memory pressure. Structs are ideal for representing simple data like points, colors, or small coordinate systems, where value semantics are desired. By choosing structs over classes for appropriate scenarios, developers can reduce heap allocations, minimize boxing, and enhance cache locality, leading to faster execution and more efficient memory utilization in performance-critical sections of code. Implementing the iDisposable interface for proper resource management is crucial in C# to ensure that unmanaged resources are released promptly and predictably. Unmanaged resources include file handles, network connections, database connections, and graphics objects, which are not automatically cleaned up by the garbage collector. By implementing iDisposable and its dispose method, developers provide a mechanism to explicitly release these resources. The using statement in C# is a powerful construct that guarantees dispose is called, even if exceptions occur, preventing resource leaks and improving application stability and performance. It's critically important to avoid premature optimization. Instead, the focus should initially be on correctness, clarity, and maintainability of the code. Attempting to optimize code before understanding its actual performance characteristics can lead to complex, harder-to-read code that offers no real performance benefit or even introduces new bugs. The best practice is to first ensure the application functions correctly, then use profiling tools to identify actual bottlenecks. Only after concrete performance issues are identified should optimization efforts be applied, ensuring that changes are targeted and effective. Staying updated with the latest advancements in C# and the .NET ecosystem is paramount for leveraging the most current performance enhancements. Microsoft continuously introduces new language features, runtime optimizations, and library improvements with each .NET release. For example, recent versions of .NET have brought significant performance gains in areas like string manipulation, garbage collection, and asynchronous operations. By actively learning and adopting these new features, such as span, T, or record types, developers can ensure their applications benefit from the cutting-edge performance capabilities built into the platform, keeping their software competitive and efficient. By diligently applying these comprehensive techniques, C# developers can consistently create highly efficient and responsive applications that deliver superior user experiences. This holistic approach, combining meticulous memory management, intelligent coding practices, and strategic utilization of advanced C# and .NET features, ensures that applications are not only functional, but also performant, scalable, and resource-friendly. Ultimately, mastering these optimization strategies empowers developers to build robust software that meets the demanding performance expectations of modern computing environments, leading to greater user satisfaction and operational success.